Hello students, welcome to series of lectures on digital speech processing. In this video you will be able to learn the classroom discussion topic on homomorphic speech processing and its introduction and what is the process of convolution based on homomorphic speech processing. So let me go through this. Alright, so this is the lecture learning outcome. See, on completion of this lecture you will be able to understand homomorphic systems for convolution. Alright, so we know that the speech can be represented as the output of a linear time varying system and whose properties are slowly vary with time. So this we already know that because speech signal is a non-stationary signal. Okay, so that is the reason we can clearly mention that. So it is a time varying system and whose properties are slowly vary with the time. Okay, so when you take the pictorial representation of that signal, so it could be like this. Okay, something like this. Okay, on a period of 5 seconds for instance. So this is the period of 5 seconds and this is the way how the speech signal will be varying according to the time. And the main problem of the speech analysis is to estimate the parameters of the speech model and to measure their variations with time. This is the very biggest challenging task for us, because as we already aware that the speech is a non-stationary signal, and if we want to estimate what is the parameters, because it is going to be varying according to the time basis, so we need to estimate the parameters of those signals. It is a very biggest challenging task for us. Okay, so this problem is often called as deconvolution. Okay, so that we are going to be doing in this lecture. So by introducing homomorphic system for the convolution, how we are going to be estimating the parameters in a smooth way. Okay, so that we can see that. So let's get started again. So the basic speech model is the short segment of the speech that can be modeled as having been generated by exciting and linear time invariant system, either by a quasi-periodic impulse train or a random noise signal. So we clearly mentioned if there is a system and we are going to be taking the inputs here, so it could be impulse function. If there is a voice signal, there is an impulse. If that is unvoiced, there is no impulse. If there is a voice, there is an impulse. So like that we are going to be taking as an impulse response as an input to the system. Okay, or else so this unvoiced can be generated by the random noise generator. So this is a random noise generator from where we are going to be getting the random noise that is also incorporating to the actual signal. So we need to estimate the parameters of the speech model, and we also know the speech is nothing but excitation convolved with system response. So I can also write like this. So if speech is S of n and which is given by excitation, so this excitation I am calling as E of n, and convolved with system response is H of n. So that is the exact meaning of that. So what we want to do here, we would like to deconvolve the speech into excitation and the system response. So that can be possible with the help of homomorphic filtering methods. So that we are going to be learning in this video. Alright, so before you learn the system, the homomorphic system, how we need to introduce. So first we are going to be seeing some of the important principles we need to consider. So in that aspect, so first we are going to be taking as a superposition principle. This we already know. So if this is the linear operator system here, and the input is x of n, and the output is linear of x of n. Okay, and similarly if you take the two signals, additive of the two signals, x1 of n plus x2 of n, and you'll be getting the linear operator of x1 of n plus linear operator of x2 of n. Or so directly I can take this as a y1 of n plus y2 of n. So that is the basic principle of the superposition, so which holds the homogeneity. Okay, that is the main principle we need to consider here. Okay, so the same thing that you are also seeing in the mathematical expression. Okay, so this is one of the important principles that we need to take care before we understand what is a homomorphic system. Okay, now so when it comes to generalized superposition for convolution, okay, so this is the homomorphic system, And here what we are doing, please look here. So here x of n is there, for instance, that is the sequence we are going to be considering, and there should be convolved. So this x of n is nothing but it is a convolved signal of both excitation and then system response. So that way you need to remember. Okay, and that can be, so that kind of signal you are giving to the homomorphic system, and you are going to be able to produce y of n equal to homomorphic of x of n. Okay, and when you want to convolve the two signals at a time, and we'll be getting h of x1 of n convolved with h of x2 of n. So what we need to understand from this slide is that, so this homomorphic system is taking x of n, so which is a convolved signal, and whose output is also convolved signal. Okay, so that way we need to remember. So for linear time invariant systems, we have the result. This we already know, y of n equal to x of n convolved with h of n. So which is given by the discrete form, like summation x of k into h of n minus k. Okay. So the generalized superposition principle is nothing but which is an addition, that is the replaced by the convolution. Okay. So x of n minus x1 of n into x2 of n. Okay. So this I am calling as the homomorphic system for the convolution. Alright. So now coming to the homomorphic filter. So homomorphic filter is nothing but homomorphic system H that passes the desired signal unaltered while removing the undesired signal. So what is the main agenda to introduce this kind of filter is that we are going to be removing the undesired signal. Okay, so that we are going to be taken into consideration only the desired signal, because it is a convolution of the two signals, right? So among the two signals, if one is unwanted signal, for instance, so that we are going to be removing. Okay, so this is the process of that. So x of n is equals to x1 of n into x2 of n. So this is the sequence I am going to be considering with. So what is the assumption I am going to be taken into consideration here is that x1 of n is the undesired signal. So this x1 of n we need to remove with the help of this homomorphic filter. Okay, so let us do what we are going to be doing here. So we are going to be taking the homomorphic, because that signal we are going to be given to the homomorphic. Obviously h of x of n is equals to h of x1 of n convolved with h of x2 of n. Okay, and if h of x1 of n, that has to be removable, and if you consider that sequence as an impulse sequence. Okay, so if you choose like that, and you'll be getting h of x2 of n equal to the same desired signal x2 of n that we are going to be taken into consideration, because from that signal only we are in a position to estimate all the parameters whatever that are associated with the desired signal. Okay, so h of x of n equal to del of n into or convolved with x2 of n, and we'll be getting x2 of n. This is the property of an impulse. Okay, if any signal that is convolved with the impulse function, the signal itself is a result. So that way we need to understand. So this is the way how we are going to be removing the x1 of n. Okay. Alright, now look into canonic form for the homomorphic deconvolution. So here we'll be having some of the characteristic system we are going to be introducing. So look carefully here, because this is the entire system actually we are going to be estimating the parameters of the speed signal. So x of n as a signal that we are going to be taken into consideration as an input to the characteristic system, that is d star of something, and at the output we will be able to see that is the x cap of n, where x cap of nothing but what? Additive property. Okay, so this convolved signal is converting into the additive property, and that additive property is the input to the linear operator. It's just like a superposition theorem principle it will holds. And here, which is the third system, this is the third system, for instance, this is the second system, this is the first system. Okay, so third system is the exact inverse of the first system. Okay, so like that we are able to see the output of the third system is that it is a convolution of the two sequences. So any homomorphic system that can be represented as a cascade of the three systems for convolution. So system takes the input combined by the convolution and transform them into additive output. The same way how we have already explained, we have given in the sentence formations. So second, that the system is a conventional linear system, and third one is the inverse of that. Same thing. When you take the example like that, and you'll be able to see this is the process actually that will be do with the help of these three systems. So this is the reflection spot, having discussed some content here. So the reflection spot is that what is the purpose of deconvolving the speech signal? Okay, and we clearly mentioned one important point here is that, so what is the problem that is associated with the normal speech signal when you contain? Okay, so because when you take the system and it is accepting the input as an excitation, because excitation is nothing but the impulse sequence we are going to be considering. Okay, so what is the main purpose of the deconvolving the speech signal is that since the excitation and impulse response of a linear time invariant system which are combined in a convolutional manner, so therefore the problem of the speech analysis can also be viewed as a problem in separating the components of a convolution. Okay, so thank you for watching this video.